Yeah, as Brad mentioned, I'm going to talk predominantly about nitrogen management research that we've been doing here in southeastern Minnesota over the last 10 years on farmers' fields. And I want to show this again, and I don't know, I think Brad, you may have talked about it, Dan may have touched on it, Fabian may have touched on it, but we're looking at, the 4 R's. We're going to focus on rate and timing. And we know that this uptake or this rapid uptake of nitrogen occurs starting around V6, and a significant amount of the N, about 70%, is taken up by the plant from V6 to R2. So if we delay some of that N application, we can minimize the risk potential for nitrogen loss. But the other reason why I put this in there, and a couple others have touched on this as well, is that when you see the amount of N that's in the dark green part, which is the leaf blades, and the olive color, which is the stalk and the leaf sheaths, that kind of maximizes around R2. And then as we put nitrogen into the grain, some of that comes from N uptake late in the season, but a lot of it comes from these translocation of nitrogen from these other plant parts into the grain. So the key thing is as others have mentioned, if you see nitrogen deficient lower leaves at R4, R5, and they're near the bottom of the plant, that does not necessarily mean that you lost yield. That's just that normal translocation of that nitrogen from other parts of the plant to the grain. It is not necessarily nitrogen limiting to the corn crop. And others have mentioned this, but you can't stress enough how precipitation changes are driving and changing nitrogen loss in Minnesota, especially spring precipitation drives nitrogen loss, and spring precipitation is getting much wetter. Here in this most recent study from comparing 1950 to 2021, the southern 3 or 4 tiers of counties in Minnesota have seen about a 25 to 27% increase. And that is what's driving our nitrogen management changes for the people that have been in this region, have been farming for the last 30, 40 years. That's why you see changes, and that's why you see some of these new rules in play. Specifically at Waseca alone, where we have about 110 years of climate data, every 10 years the National Weather Service calculates a new 30-year normal. So for total precip, if you go back to the 1941 to 1970 period, that's right there, that was 30 inches of total annual precipitation, including snow. Last time we did this was in 2021, after the 2020 growing season. We are now at just under 38 inches. So that's a significant increase, and that water has to go somewhere, and some of it goes into the soil, some of it runs off, some of it percolates and drives nitrogen loss, some of it results in denitrification, and our plants are becoming more efficient. It's driven some yield increases as well because we're getting more rainfall. So as Brad said, I'm going to talk primarily about this research that we've been doing in southeast Minnesota. And about 10, 11 years ago, Kevin Keener came to me and he said, Jeff, I've been working with a couple farmers on nitrogen management, and I want to know if you'd be interested in doing N-rate trials on some of these farmers' fields and working with them in kind of small groups with the farmer, their crop retailer, who usually helps them make the decisions on what nitrogen practices they should use, and also in some cases, their independent crop consultant, if they have one, or their other ag advisors. Maybe it's their seed retailer who helps them with nitrogen management. And I said, yeah, I think this is a good idea. And our goal was to work with these smaller groups and try to drive or get them interested and engaged in nitrogen research, and hopefully build and gain their confidence in our recommendation systems and our guidelines and the best management practices that others have talked about earlier today. So what we're measuring in this study is the effects of nitrogen rate and application timing on corn yield, nitrogen use efficiency, net return, and residual soil nitrate, with residual soil nitrate being our kind of water quality parameter, as Fabian just talked about extensively. We're also calculating the economic optimum N rate, or EONR, which others have mentioned, and I'll use the term EONR and MRTN, or maximum return to nitrogen, kind of simultaneously. They're very similar. So the methods of this study, from 2015 through 2021, we had 24 site years on farmers' fields. There were 7 N rates plus 3 split application treatments, and the split applied treatments were applied at V4 to V6 typically, somewhere in there. But in 2022, we changed the study, we added 2 more treatments, and we really wanted to focus on this difference between pre-plant and split applied. So we actually now have 5 pre-plant treatments, 5 split applied treatments, and we have 1 control and 1 ESN urea blend. What this allows us to do is actually calculate not only the optimum N rate for both pre-plants and splits, but also look at the effects it has on yield as well. When we only had 2 or 3 treatments, we could only really look for a yield difference. We couldn't really determine whether it needed less or more N when we did split application. This study's been funded by the Clean Water Fund through the Department of Ag, and Dawn Bernau has been critical in helping me and working with this as well as Kevin Keener. So this is just an example, and you've seen a whole bunch of these today, as you've seen. You got yield on the y-axis, you got total N rate on the x-axis, and wherever we have total N rate, we're going to include any nitrogen that came from other sources, whether it was fall-applied MAP or DAP or AMS in the fall, whether it was a starter fertilizer nitrogen that was included in the spring. We're going to include all those things in that total. So we're not excluding those, they're going to be included. So we've got pre-plant N rates in the black circles, and this is the means of the individual treatments. We calculate a response function. We use a little statistics and calculus. We come up with the diamond there, which is the optimum N rate. In this case, it was 188 pounds for corn after soybeans in Grand Meadow. And we also had 2 split applied treatments, the red triangles and the blue triangle. And at this site, those split applied treatments produce greater yields than pre-plant at those N rates, and it actually looked like that blue treatment produced a very similar yield with much less nitrogen, and that's what we want to get at the later part of this talk. So, take 13 sites, they're all corn following soybeans, and you plot that response curve, and you put a dot on it where the optimum is, and this is the yield from all 11 sites, or these are 13 sites. This is the total N rate. It goes up for corn after beans from 0 to 240. This gray shaded box is what we currently recommend in 2023. It hasn't changed too much, has it, Dan? 130 to 150 is that acceptable range. You see that we've got a few sites that fall within that box, about 3 sites that are just below it, and 4 or 5 sites that a couple of them are close to the maximum and a couple of them are greater than that. So what's interesting is these 4 or 5 sites that are greater all pretty much came from Grand Meadow. And Grand Meadow is in the eastern part of Mower County, but what it's unique to is that it's actually a poorly drained tiled field. It's right at the very edge of the karst region and the deeper lust soils that are well drained, but it's also a soil that extends well into northeast Iowa, and it's very common, and it extends well over into the western part of Mower County as well. So these are soils that are denser, they have poor drainage, and they have kind of a dense layer that suspends water. So they really have a lot more denitrification, and leaching isn't as big of a factor. But what makes it interesting and why Kevin is researching this is that the drainage from this field goes into water bodies and into watersheds that are in southeast Minnesota. So that's part of its interest. So when we look at these sites that needed more nitrogen, what did they have in common? Well, they were generally, as I said, in that Grand Meadow area. They also had very poor yields with 0 nitrogen, considering this is corn after soybeans. And we would typically expect about 150 bushels of corn with no nitrogen in corn after soybeans. The other thing, we talked about organic matter earlier. These soils actually have very high organic matter, 4.5 to 8.8%, these soils in Grand Meadow. Compare that to the lust soils in Elgin, Green Leafton, and Utica, which are anywhere from 3.7 to 4.6%. So if you're going to think about, well, I'm going to adjust my nitrogen rate based on organic matter, these soils actually need more even though they have higher organic matter. And it's all driven by the potential for nitrogen loss. In this case, clearly denitrification is the loss mechanism that's driving nitrogen loss. So what about rainfall? This is a crazy chart, and it's monthly total rainfall at every site across the top for these corn following soybean sites. and it's got an April through September total, and it's got the MRTN, or the economic optimum N rate, for each individual site. And what I've done is I've set this as a % of normal rainfall. So whatever was normal for that month in that year at that location. And when you see red boxes, those are months that had greater than 150% of normal rainfall, or 50% more than normal. If the boxes are yellow, they fall between 125 and 150. So if you see sites that have a lot of red boxes, like this one here in Grand Meadow in 2018, and this one in Grand Meadow in 2019, and over here in Elgin in 2018 and 19, those are sites that were very wet. Now, obviously, we know that excessive precipitation in the spring probably drives more nitrogen loss than it does in the fall or in the summer. But what happens is when we keep getting these really wet falls and then we go to another field that's just adjacent the next year, I think there is some effect that this happens over time when you keep getting wet years and wet years and wet years in a row. And we'll talk more about that later. But when we look at some of these sites that had very high MRTNs, this one here, 203, really not a wet growing season. This one here, 198, definitely a very wet growing season. And you see a couple other sites over here that also fall in that category. But it doesn't explain them all. Now, these are the corn after corn sites. Now, in the corn flowing soybean sites, we actually did pretty good. 7 of those 11, or 7 of those 13, our range was pretty close to where the optimum was. But what we see in the corn on corn sites is there's a much wider range, anywhere from 100 pounds to 270, and 270 was the highest N rate we had. And we also see different responses. We see low sites that have very low yield with no N, which we'd expect in corn on corn, but we also see sites that have very high yields with no N, in this case, almost 175, 180 bushels. So clearly, corn after corn is a bigger challenge and more difficult to determine what the optimum N rate is, and there's more variability year to year, site to site. You know, we can look at these sites here that needed a lot more N, and we can say, well, they had really poor yields, but maybe what we should be focusing on in corn are these sites that had really good yields with no nitrogen, and they generally needed less or are near our recommendation. So it suggests that the environmental conditions from those sites was ideal for mineralizing N, and there was also ideal for not losing very much nitrogen during that growing season. So what do you see when you look at these corn on corn sites from a precipitation standpoint? You see a lot of red. And these were extraordinarily wet years. Harmony in 2016 and Harmony in 2018, this was the wettest growing season and total annual precip in the state of Minnesota's history. It came in at 177% of normal just from April through September. And you see back-to-back years here with wet conditions. And what do you see is, here's 2 really high end demand years. They're in a similar location. They're not the same field. They're adjacent fields, but they're coming off wet years with a previous wet year. And I think that this is something that we have to pay attention to in the future, is we can help predict if we're going to need more N the next year, maybe by what happened the last year. And our old colleague at the U of M, soil physics, what's his name? Satish Gupta used to talk about that the amount of water that was in the profile the previous fall also affected what our nitrogen management conditions and our loss mechanisms were going to be like the next year. And I think there is some truth in that, and we need to pay more attention to this. But when we look at these just from a monthly standpoint, clearly some of these years that needed a lot of N had very wet springs and had wet other parts of the growing season. And you see that over here in this Utica 2019 site and Utica 2018 site as well. So that can help us explain why some of these sites need greater nitrogen rates. So we'll talk a little bit about split application. And as Fabian said and Dan said, split application doesn't always give a big return on investment. It doesn't always give a yield increase. Out of these 24 site years, only these 5 had a significant yield increase with split application, so that's about 21% of the time. And actually only one of those 5 really had a wet spring, which is kind of interesting because you'd expect that wet spring would have drove more losses and would have been more likely to have a good response to split application. But what it is that go back to look at some of these sites, and it's back-to-back years that tend to drive, back-to-back wet years are driving some of these sites where split application is superior. So we'll look at the residual soil nitrate as kind of our water quality indicator, and as others have shown, this is the 0 line, or this is if we apply X N rate minus what we calculated was our economic optimum. So right here is if we put on the exact amount. Anything to the left of that is suboptimally fertilized, and anything to the right of that is more N than we need. And as others have shown, our residual nitrate stays really low, and really there's no advantage to putting on much less than we need agronomically. And it's not until you get within maybe 30 to 40 pounds of the optimum that you start to see this line bend upward and you start to see more variability in the data. And then as you get 50 pounds and greater above what's optimum, that's when you start seeing a lot of variability and this line really start moving upward. So that's kind of where we want to be from an environmental standpoint, from an agronomic standpoint, and from an economic standpoint. So to summarize these first 6 or 7 years, if we would have applied something around the maximum of our acceptable range, which is about 150 pounds of N for corn falling soybeans, about 10 out of 13 years, we would have either optimized yield or economic return, and we would have been fairly friendly to the environment. But we would have over-applied on 3 and we would have under-applied on 3. For corn after corn, though, the UNRs ranged from 100 to 270. Clearly, it's much more difficult to identify what the optimum N rate is in that circumstance, but excessive precipitation did explain a lot of these very high years in corn on corn, but there's also other factors in play. The soil N supply, the potential for mineralization, the Grand Meadow site, clearly that poorly drained site takes more nitrogen than the well-drained lust soils in the true karst region. Maybe there's some compaction going on. There's certainly that compacted dense layer in that Grand Meadow soil down at about 2 feet. That's resulting in more denitrification. So we need to look at other tools to help us with this corn on corn optimum N rate. From a split application standpoint, as I said, about 20% of the time, it looked like split application was better. And the impact of this study, we did a survey, or Dawn Bernau did a survey in 2022 of the participants. And this included not only the farmers, but their ag retailers or their crop consultants. And they found that 46% of them plan to reduce their nitrogen rates after seeing and looking at this data and being on these sites, seeing these fields on their farms. 92% were somewhat or extremely likely to discuss the results with farmers and other ag advisors, and 90% made N management changes based on the results. Now that might have been the timing, it might have been nitrogen source, it might have been nitrogen rate, it could have been one of many factors. I will say that all these sites had pre-plant or had urea as the primary nitrogen source, and generally we used a urease inhibitor because sometimes it was applied and incorporated and sometimes it was not. So just to keep it from potentially being lost, we usually put a urease inhibitor with it. So now we'll move into the second part of the study. So it was evident in 2019 and 2020 that we wanted to focus more on the split application versus pre-plant. And I talked to Dan Kaiser, and Dan said, you know, we really don't have a lot of data in the database where we actually have N rates of both pre-plant and split at the same site in the same environment each year. So we started this in 2022. 2022 was a year where it wasn't a wet year, but there was at least 1 month, and it was usually July, early July, that it was extraordinarily wet at most of these sites. So there was some potential for losses, and it probably was driven as much by denitrification as leaching. So what we have here is each of these dots represents an individual plot, 4 replications of 5 rates plus a control, and the controls are the same for both pre-plant application, which are the black circles, and the gray triangles are the split N application. And the split was applied as about 2/3 of the N was put on at planting, and the last third was held off until side dress. And that last third was generally either 50 pounds for corn after beans or 60 pounds was held for corn after corn. We had N rates from 0 up to about 270 or 250, 60 for corn after beans. These are the two sites in 2022 for corn after beans, Grand Meadow on the left, Elgin on the right. Over here in Grand Meadow, it took either 150 or 160 pounds of N to optimize yield, but you see the line for the split application is greater, and we had about a 6 bushel yield advantage, and it took about the same amount of N. Over there on the right at the Elgin site in 2022, we produced the same yield with these different approaches, but the split application actually used considerably less nitrogen, kind of shockingly less, 72 pounds at this location. We go to the corn on corn sites in 2022. Here is Harmony, very similar yields, but about almost 30 pounds less when we use split application. Over here at Dover, and the Dover site is unique. Someone mentioned earlier, did we have any sites that had a cover crop? So the Dover site all 3 years was corn following sweet corn with a cereal rye cover crop planted after the sweet corn was harvested. At the Dover site, we only needed between 112 and 135 pounds of N to optimize production, and we produced about exactly 233 bushels with both systems, but it took about 23 pounds or 22 pounds less with split application. Now this was in 2022 when we had some wet months, but generally not a wet growing season. Now when we go to 2023, we're back to corn following soybeans. Most of you remember 2023 as being a very, very dry year, correct? So was this a year that we would expect split application to have an advantage over pre-plant if it's going to be a dry growing season throughout the growing season? Probably not, and it wasn't. The responses from N rates or optimum N rates to yields are virtually identical for both of these sites. There is some difference in total N need. The Grand Meadow site almost always needs more N than the Elgin site, which is a D+, 125 to 137 versus 169 to 174. We look at the corn on corn sites. This Harmony site was really unbelievable. 80 pounds produced about 200 bushels, and there really wasn't a lot of carryover residual nitrate in that field from the previous year. It was just a very unique situation. Over at Dover, we needed a lot more N in 2023 when it was dry. It actually took almost 200 pounds to 210 to produce 242 bushels. But what was interesting, we looked at the residual soil nitrate from that site, is we had a lot of nitrate in the top foot or two of the soil that plant couldn't use. It was so dry at that site, the plant was taking up water way below that nitrate that was in the top 2 feet. It was taking up moisture at 3 or 4 or 5 foot depth. And that N was what we would call positionally unavailable. So it was kind of a circumstance of the cropping year that drove that higher N demand at that site. But actually is amazing that we got 240 bushels there considering how little precip that site saw that year. Now we'll go to 2024. Most of you are going to remember this year was recognized for probably one of the wettest growing seasons in southern Minnesota history, especially in June and late May and early July. This is the Grand Meadow site. We had 15.3 inches of rain in May and June. Pre-plant is in black. Split application is in gray with the triangles. The EONRs are not that different. They're only separated by, 8 pounds? But we produced 12 bushels more yield with split application, and it took almost 100 pounds more N to produce the similar yield that we would any typical year, which gets to the fact of how much nitrogen was lost in this field in that extraordinarily late May through June period. Not surprisingly, there was not a lot of residual soil nitrate left in that profile after harvest. Here's all the N rates. These are the pre-plant ones. These are the split ones. Here's 20 pounds of residual soil nitrate in a 4-foot profile. Very, very low numbers. I would say 40 to 50 is a typical background level. So when you have a very high demand, you're coming off a really wet year, you're not going to have much N left in the soil system. Doesn't mean that it's not going to be, there's not much left to lose. And of course, this field's going to go back to beans, so it's not like it's going to be carried over for the next year anyway. We look at the Elgin site. This was just as wet, 10.7 inches of rain in June. The pre-plant is in black, 171 pounds, 230 bushels. The split was 133. So this is 2 out of 3 years where this site got by with a lot less N when we did split application compared to pre-plant. This is the Harmony location. The Harmony location had 11.8 inches of rain in May and June, but it was only about 110 to 120% of normal in any given month. So it actually saw quite a bit different environment compared to these other sites that had extraordinarily wet and extended saturated conditions through a lot of late May and June. So the nitrogen loss potential at this site was a lot less. It took either 181 or 185 pounds. There really is no difference. It produced either 287 or 289 bushels. So here's a classic example of where people think that, okay, I'm going to shoot for 300 bushels of corn. I'm going to think that I got to have 1 pound of N per bushel, so I need 300 pounds. This is a case where we grew nearly 300 bushels with 180 pounds right within our recommendation guidelines. Now, what will be interesting to see is what happens to this site next year, especially depending upon what this spring weather looks like. This site had 27 pounds of N applied in October as DAP, and we credited it in this total. But I'm sure a lot of it or some of it was lost, but the PPNT that we took in April still was less than 6 part per million, which is a bit puzzling when you think about it, Dan and Fabian. You'd expected that one to show a credit, and it didn't. This is the residual soil nitrate for that Harmony site. And again, look at how low some of these values are, even up to 267 pounds of N, which is considerably 80 pounds more than we really needed to optimize production. So applying much less than what's agronomically optimum really is not having a huge impact on the potential for loss and the potential for water quality degradation. It's not until we got up to 327 did we see that we left a lot of N in the profile. This was our Dover site. This is corn after sweet corn with a wide cover crop. It only took 125 or to 135 pounds of N to either produce 277 with the split application or 271 with the pre-plant. This site did have a PPNT of 7.6 part per million, so it would have gotten a 35 part per million credit. And when you add that to what our UNR was, it kind of makes sense. That kind of makes sense to me. This site also had 10 inches of rain in June, so the split application was better. It took 10 pounds less N and it produced 6 bushels more. So we'll look at the precip by month for these last 12 sites. You see 2022, we get there and here and here and here. Not really a lot of really wet months, but at these 3 sites, there was at least 1 month that was considerably wetter than normal and maybe another month that was kind of wetter than normal. When we look at 2023, dry, dry, very dry. Total growing season precipitation, 46% of normal at Harmony. 44% normal at Dover, 44%, less than half of what was normal, and it still yielded 240 something. That's hard to believe. Now look at Grand Meadow in 24, 191% of normal in June. Elgin, 205, Dover, 187, really wet Junes. Certainly can drive not only leaching, but denitrification. And that explains why, especially at Grand Meadow, we needed significantly more N than we normally would do. But it doesn't mean that we need to apply it up front. It means that we need to adjust in season. So the next thing I want to do is, so the question is, can we apply less nitrogen if we split apply? So this is all 12 sites from 2022 through 2024, and I've taken the economic optimum N rate as affected by rotation and application timing. So these are the optimum N rates for continuous corn. This is for corn soybean. This is the blue one is for when it's applied at planting. This is when it was split applied. And you see there's some big negative tails on this one and positive tails on this one. This is that Harmony site that only needed 80 pounds for corn on corn. And this is the Grand Meadow site from this year that needed 250 for corn falling soybean. If I remove those sites, and I think it's justified to remove them because we wouldn't make a recommendation for 80 pounds of N for corn on corn. And we can't justify a recommendation of 250 for corn falling soybeans, even if we know it's going to be a wet year. If we remove them, we see it tightened up quite a bit, but a lot of similarities. We did a pretty good job of being right around our guideline for split applied N for corn after beans. And when we applied at planting, it was a little bit wider and it seems to have taken more N. That bar is taller, it's up higher. And corn on corn takes more N, and as in the earlier study, part of the study, there's more variability in the optimum N rate in corn on corn. It's harder to figure out what the right rate is. Another way to look at this is like a probability distribution. So now I've taken the number of sites that fall between, if I take the EONR from N applied at planting and I subtract the EONR from split applied N, if the difference of those two EONRs is minus 12 to plus 12, it falls in this column. 8 of the 12 sites were in this column. If it's 12 to 36 pounds difference, it falls in this column. 36 to 60, 1. 60 to 84, 1. So when we think about differences, being scientists, we think about statistical differences, we think about economic differences, agronomic differences, and I think we need to start thinking about environmental differences. When I look at this data, if it's in this column, it's not different. There's minus 12, plus 12, it didn't matter. If it's in this column, maybe it's different. 12 to 36 pounds less if we split applied versus applied pre-plant. If it's in this box, there's one site, it's definitely different or probably different. And if it's in this box, it's definitely different. So to think about this from a probability distribution, 8 of the 12 sites, there were no differences. 4 of the 12 sites, we could say with some confidence that was split application was better, both agronomically, economically, and probably environmentally. And if we just take these two boxes, I think you can say definitely and very strongly that those are different, and that'd be 1 out of 6. Fabian showed this from the study that they did with Pioneer, where they looked at the sites across the Midwest. Here's our here's our residual soil nitrate to a 4-foot depth. We look at the 0 line where we're going to apply exactly what's recommended after the fact when we already know what we needed. And you look back here and you see this is a very flat line. It's somewhere around 20 to 30. And as you get within 25, 30 pounds, it starts to bend up. But it's still less than 50 pounds left in the profile at applying exactly the MRTN or the EONR. And then as you go up, you start to see greater and greater amounts of residual soil N, and you get a lot more variability, which says there's a greater risk for the potential for nitrogen loss. And there is a difference between this split applied line and the blue one, which is the all pre-plant, but it's really driven, I think, by those 2 data points, which just seem to be outliers, but I left them in there. So I don't think there's necessarily a big difference between split applied and pre-plant when it comes to the amount of nitrogen that's left in the profile afterwards. Am I about done? Good answer. So to summarize, applying N rates within the MRTN acceptable range, optimize yield or economic return in 8 of the 12 sites during this period. 2 sites needed less, 2 sites needed more. When N was applied pre-plant, 7 of the 12 sites needed more N. So split applications seemed to reduce our nitrogen rate, and when we looked at it from over those box plots, it was about 20 pounds, averaged across all 12 sites, but only really 4 of the 12 sites had major differences. When did split application do well? It did really well in 2022. Every site had at least 1 month with with excessive rainfall. And it was usually July. One of them was August. So in 2022 was a good year for split application, and 2024, which was an exceptionally wet, late May through early July or spring period, that was a year when split application did really well. And obviously split application made no difference in 2023 when it was really dry. Risk for nitrate contamination, split applied N rates had a little bit greater MRTNs, and it often resulted in slightly greater residual soil nitrate, but it wasn't very large. And it was primarily driven by 1 or 2 sites. So the last thing I'm going to talk about before I stop is we did look at some tools that could help improve our N recommendations in this study. And this could be a whole 45-minute talk, but I'm just going to narrow it down to one slide with some bullet points. We looked at spring soil N tests, and I'm just going to focus on the 2022 through 2024 period. We could need to go back and look at all the data together yet too. But the pre-plant N test, 0 to 2 foot, 4 of the 12 sites had PPNT values that were greater than 6 part per million, so they would have been given an N credit or assigned an N credit for those sites. But when you looked at that N credit, only 1 of 4 of those sites really agreed with what the EONR was. And it was that one last site in 2024 at Dover where we had corn after sweet corn with a cover crop. And that makes sense. Whenever you're going to put corn after corn or corn after some crop that's harvested early and it's going to be there for a long fallow period, it would make sense to go out there and take a pre-plant N test or a pre-side dress N test. But the other 3 sites, even though it had a credit, it didn't really agree with what the EONR was. The PSNT test, the 1 foot test at side dress time, using a 25 part per million critical value, which is what Iowa generally uses, was accurate to within plus or minus 20 pounds per acre, about half the sites. And it hit them all in 2022. But it didn't do very well in 2023 when it was really dry, and it generally predicted an N rate that was less than the EONR was at the end of the year. So the soil test said we were above the critical value well before we got to the EONR. Excessive precipitation explained greater demand of fertilizer N about half the time. It was better on the poorly drained soils than on the loess soils. It was better in corn after corn. And I think that makes some sense because it also depends upon what happened the year before if it's corn on corn. And if we have these really wet falls, it's clear, I think, or there's certainly some evidence that it affects the next year. If this field was in corn, it was a wet year, it's going to corn the next year, it's likely to need some more N, especially if the next spring is going to be wet. And you can adjust for that with a split application. So that is one option from a management standpoint that you can do in season. Other things that we looked at aerial imagery. In fact, we had a group of individuals who were taking our data. They were running their drone across the field every couple weeks. They were trying to develop an algorithm for site-specific in-season application. I think it works, but it's only really going to work as a rescue treatment because I don't think you can predict, as Dan said or Fabian said, you can't make a recommendation when the corn is V6 or V7 when you should be side dressing. That's going to be very accurate. You have to wait until the crop really starts to suffer, and that's probably not going to be till V10 to V14. It doesn't mean that you couldn't put a rescue out there, but it's not going to be a management technique that you're going to use on every acre every year. Sensors like the SPAD meter, they're time consuming, they're difficult on a field scale. The on-the-go sensors are better, but again, it goes back to like the imagery. It's only really going to work well when the crop gets a lot bigger, and by that time, you've accepted a lot of risk in managing with that system. Basal stock nitrate test, that's a post-harvest. How did we do? In this database, it was wildly variable, especially among replications at the same N rate. It would go from below optimum to way above optimum, all in the same N rate. And this is in a 1 acre field or 1 acre plot. So very inconsistent, and I don't like it because it's messy. It leaves a bunch of plants laying out in the field with their ears still attached. And it's hard work. So the acknowledgements, this study was funded by the Department of Ag through the Clean Water Fund and the U of M Experiment Station. Special thanks to Dawn Bernau and Sarah West, who helped with this project a lot. Every time at harvest, they're always out there helping us in the spring when we're setting it up. Kevin Keener, it was his idea, and he also helps. Michael Cruz, who was here earlier, not sure if Michael's still here, and Kyle Holling and other research interns and stuff, others who help with the field work. And also thanks to our collaborators and the ag advisors and the farmers that were involved in the study. Do we have any time for questions? We do. Yeah, so the question was, there a couple examples where our optimum nitrogen rate was lower with a summer crop? Yes. 2 of the 3 years where we had sweet corn as our previous crop, we needed what I would say on the lower end of our recommendations. But the other year it was very high, but that other year was the year when we had the severe drought. And I think if we would have had normal rainfall, we could have got by with a normal amount of N that year too. And our colleague on campus, Carl Rosen, has done N rate trials looking at the amount of N after sweet corn across the state, and he's found similar results, where it's probably more like corn after beans is how much N is needed in those situations versus corn after corn. And it's probably a combination of less biomass with sweet corn versus the amount of biomass you get with field corn. And then you have this extended fallow period with or without a cover crop.
It's more like a corn soybean.
Yeah, I'd say it's more like corn soybean, or it's more like corn after a small grain. It's going to not need as much N as corn on corn. And I see the same thing in studies with corn silage. And I think it's because you're taking away all the biomass and you're minimizing the amount of immobilization potential the next year, and you're harvesting basically a month earlier most of the time. So I think you can get by with less N in a corn where it's corn silage too.